Hi, I'm Nur Adawiya and I'll be explaining my medical electronic project demonstration. So now I'm going to explain stage 1 pre-amplifier. For this stage, it uses TL072 op-amp configured as a non-inverting amplifier. The input signal first enters through X1, which is also the microphone. And since the signal entering is very weak, we cannot process it directly, so we need to amplify it first. The signal then passes through capacitor C1, which blocks any unwanted DC voltage and only allows AC signal to pass through. Next, the resistors R5 and R6 creates a bias voltage of about half the supply voltage, which means it helps the op-amp work properly with a single power supply. The signal is then amplified to T072. Here, the gain of the amplifier is determined by resistors R2 and R3. So, using this formula, AV equals 1 plus RF Rn, and then we substitute the values where RF is 220 k ohms and Rin is 10 k ohms, we get 23. This means that the input signal is amplified around 23 times. Finally, the capacitor C2 and capacitor C3 helps reduce and remove unwanted noise, which means it improves stability. For C4 over here, it removes DC offset before sending the signal to the next stage. This is my stage 1 circuit. So you can see that the input is 200 MV at 1 kHz and the supply voltage is 9 volts. At this unit, my output voltage will be 3.356, which can be shown in my next table. Here you can see my graph. The green increases from 10 Hz to 100 Hz. After that, as frequency increases, the capacitive reactance decreases, allowing more signal to pass through and increasing the gain. After approximately 100 Hz, the gain starts to decrease. My upper cut and lower cut frequency, my lower cut frequency is 24 Hz, whereas my upper cut is 1490, which can be used to calculate bandwidth. Now, I'm going to explain stage 2 voltage adjustment. After the signals goes through stage 1, it enters stage 2. So for stage 2, it also uses TL072, but this time it's considered as a voltage follower. And since it's a negative feedback loop, it reduces overall voltage gain. Unlike the first stage, this one doesn't really amplify the signal. Its gain is about 1, so the signal stays almost the same size. Instead, what this stage mainly does is adjust the DC operating point of the signal. For resistors R9 and R10, it creates another reference voltage, and P1, the potentiometer, lets us adjust the voltage if needed. So basically, for this stage, we're making sure the signal is centered at the correct voltage before it enters through the next stage. If we skip this stage, the signal could get clipped or distorted later on. Here, this is my stage 2 circuit. My input is TP2, whereas my output TP3. Without changing the function gen and the supply voltage, my output can be adjusted using the potentiometer. Since there's a gain of 1, we have to make sure that the signal remains within the 0 to 9 volt operating range and prevents the clipping before entering the low pass filter. For my input, the approximate value will be 4.6, but I've measured it and my value was 4.56 volts. Next stage is second order low pass filter. The next stage uses CL072 op-amp together with resistors and capacitors arranged in silent key configuration. The purpose of this stage is to remove unwanted high-frequency noise while allowing low-frequency signals that we actually want to pass through. That's why it's called low-pass filter. So, the formula for the cutoff frequency is usually Fc equals 1 divided by 2 pi Rc. But although the cutoff frequency depends on all the resistor and capacitor values in the active filter, this equation shows the basic relationship. So once I've already calculated with all the resistor, the estimate cutoff frequency is 996 Hz. One advantage of using the second order filter that it removes unwanted frequency much more effectively. A first order low pass filter has only minus 20 dB per decade, whereas a second order low pass filter has minus 40 dB per decade. This means high-frequency noise is reduced much faster, resulting in a clearer output signal. After filtering, capacitor C8 over here removes any remaining DC component before sending the signal to the next stage. So overall, stage 3 improves the quality of the signal by removing unwanted noise while keeping the useful part of the signal for the next stage. Next, I'm going to show you stage 3 circuit. Here, my input is connected to TP3, whereas output TP4. TP3 input can be affected by how you adjust the potentiometer, but for this measurement, we have to keep a constant 5 volt. Next, I'll be showing my table for my output. For this table, it shows the frequency response of our second order low pass filter. The input frequency gradually increased from 20 Hz to 4000 Hz. You can see that at 800 Hz and 1000 Hz, the voltage decreases. This is because a low pass filter blocks any unwanted high frequency noise. Therefore, I will show you the graph in the next slide where you can see there's a curve after around 1000 Hz. We have the last stage, stage 4, which is the audio power amplifier. This stage uses LM386, which is a low voltage audio amplifier. Comparing this to the previous stages, which uses TL072, the signal is not powerful enough to drive an output device as a speaker. That's why we use LM386. The filter signal first passes through capacitor 13, which is a coupling capacitor. Its purpose is to block any DC voltage and also allow AC signal to pass through. After it passes through this capacitor, it goes through pin 3 of LM386, which is a non-inverting input. Inside LM386, the signal is amplified so that it has enough power to drive the output. The LM386 has a default voltage gain of 20, which can be written in this. And the potentiometer over here, P2, in this stage, it allows the output level of volume to be adjusted. By turning the potentiometer, we can increase or decrease the amplitude of the output signal. Then you also notice there's R17 and capacitors 15 connected near the output of LM386. These components are there to form a stable network. Its purpose is to improve the stability of the amplifier and also prevent unwanted oscillations when driving a speaker, especially at high frequencies. Finally, the amplified signal leads through LM386 through pin 5 and passes through the output coupling capacitor. At this point, the signal is much stronger, cleaner, and ready to drive the load. Overall, the purpose of this stage is to provide a final power application so that the processed signal can be used effectively by the output device while maintaining a stable and reliable performance. Now I'm going to show you my stage 4 circuit. As you can see here, when I rotate the potentiometer, the amplitude of the output waveform change. Turning it clockwise increases while turning it anti-clockwise decreases the amplitude. But this waveform remains a 1 kHz sine wave, so only the signal level change. The potentiometer is used as a volume control. It allows us to adjust the output level manually. Rotating it changes how much of the amplified signal reaches the speaker, making the sound louder, softer, without changing the signal frequency. In conclusion, that's the end of my presentation. As you can see, each stage has its own important role. The preamplifier boosts the weak signal. The voltage adjustment stage provides the correct operating voltage, whereas the low pass filter removes unwanted noise. Lastly, the LM386 provides the final power application with adjustable volume. By combining all 4 stages, we're able to produce a clean and reliable output signal. Thank you.